Good morning, everyone. This is March 17, and this is a St. Patrick's Day. And in New York, it's St. Patrick's Parade, just going like 10 streets north of us. But here we have the first in-person seminar of this semester, and we're very glad to see Pawel Pralat with us from Toronto. He's from Toronto Metropolitan University, and he will be giving talk on semi-random process. Thank you, Pawel, for giving a talk to us in person.
Yeah, thank you so much for inviting me here. Pleasure as always, not the first time, not the last time, hopefully, in this location. So yes, indeed, I will be talking about semi-random process. And this is the process that was kind of introduced recently, but it generalizes, as you will see in a moment, a lot of other processes, and including famous Erdős-Rényi random graph process that people are interested in for many years, and thousands of papers were written on that topic. So let's just jump straight, if I can move my slides, hopefully. So I like this process because it's kind of combines randomness as well as combinatorial game theory. So you can think about this as a single player game, if you like playing games, so you can just play with yourself. So you start with n vertices, and the graph is empty, so you don't have any edges in your graph, and vertices, and now one square arrives uniformly at random on some vertex. So every vertex has the same probability of receiving a square, but one square is placed randomly on the board. And now you are the skillful player. You can connect this square to a circle and create an edge this way. So I'm putting a circle on the vertex V, and now an edge UV is created. And now, of course, you say, okay, that's a boring game. What are we trying to achieve? Well, you pick your favorite monotone property, and then you try to achieve this monotone property as quickly as possible. So that's kind of like the game we'll be playing. So think about, for example, I don't know what your favorite monotone property is, but let's say you pick a perfect matching. So you would like to create a perfect matching in your graph. That's a monotone property, because if I achieve the perfect, the existence of the perfect matching, of course, future edges are not going to destroy it. So that's definitely a monotone property. But you can think about Hamilton cycles. I don't know, you can think about chromatic number being less than k. Pick your property you want. And I guess monotonic is actually not needed. It's useful to have because if you achieve it, you don't want to lose it in the future. But if you just want to play till you achieve any property P and then stop, then of course you don't need monotone property anymore.
So monotone means that if you increase the number of vertices that preserve?
No. If you add more edges, you preserve the property. So from that perspective. So yeah, some of the properties could be also monotone with respect to adding vertices, but here you want edges. So again, it's just, I don't know, mentally it's easier to think about say, chromatic number at least k. You add more edges, you only can increase the chromatic number after adding edges. You cannot decrease it. So maybe it's good to keep those properties in mind, because you're not worried that once you achieve it, at some point you might lose it. But I guess again, if you just stop the game at that point when the property is achieved, then that's fine. You can still play the game and try to do it. But monotone, just making sure that eventually you have the property, and the question is, how long does it take? And once you have it, you will have it forever. All right, so I don't know. So let's say we play perfect matching. So this is just a cartoon, of course, not really an interesting process to watch, but just to see what's really happening. So at some point, vertex U gets the second square lands on the right top corner, and now I'm connecting this to vertex V. And then another square length on, and maybe something to point out is that in each round, independently from the whole history of the process, a square arrives on the random vertex. So of course, at some point, squares will start appearing on circles, and also squares will appear on squares. So it's like a coupon collector process where some vertices will be selected many times, but some other vertices will be not selected at all. So that's how it goes. But you are placing circles whenever you want. So that is not that's your choice, right? So here, I'm not so happy with my square landing on a circle, but still I could try to use that edge to help me with constructing the perfect matching, because I don't know exactly what will happen in the future, right? So here is another square, and I guess probably it makes sense to connect it to the isolated vertex, but then as we see, as we discussed, some square lands on another square, but it's actually not so bad, because now I can finish the job with my perfect matching, and I'm happy, right? So this is one of the games, but again, you can play this game using different strategies, or different strategies and different properties. So this process was introduced relatively recently. It's 2020, and already attracted kind of a little bit of interest, but it's still early on, and many, of course, open processes are not investigated yet. So there's still, a lot of open problems in this area. So one observation is, and I already mentioned about that, is that this process is nice because it generalizes a lot of existing random processes. Like, for example, nobody can stop the player to play randomly. So if the player plays randomly, then essentially in every round, a random edge occurs on the board. So I have this classical Erdős-Renyi random graph process, which was introduced by Erdős and Renyi in 1960. So this is a well-known process that people care about. But in general, of course, playing randomly is not a good idea. So, for example, in a perfect matching scenario, it would take us n log n rounds, because if I play randomly, there will be, by coupon collector problem, there will be some vertices not picked at all by any of the squares and any of the circles if I don't play in a smart way. But if I do play in a smart way, and again, we'll see it in a moment, I can achieve actually, perfect matching very, very quickly in a linear number of rounds. And that's just one example. I think at least one or two more will be mentioned during this talk. Other processes such as K-out process also can be mimicked by the semi-random process. So it's really kind of generalization of many things that people care about. And as usual, I don't know if you remember my last talk here, but I always talk about asymptotic behavior. So I would like to understand what happens if n tends to infinity. And also, this is a random process. So as always, we care about events that hold asymptotically or more surely, meaning that I would like to show that the probability that something good happens tends to 1 as n goes to infinity. So this is always necessary, right? Because, for example, if you are super unlucky, I want to create a perfect matching, but I'm super unlucky, the process always gives me the same vertex. That would be, of course, pretty bad. There's nothing I can do if squares land on a single vertex. But of course, this happens with exponentially small probability, even more than even smaller than that. So with probability 1 over n, a given vertex is picked. So the probability that I see it n times in a row is 1 over n to the power of n, some extremely low probability. So I'm definitely not interested in those weird events that will not happen asymptotic and mushroom. So that's kind of the scenario we have. And I hope you will stop me at a time if there's something not clear. So this is kind of all standard, but yeah, if you don't see these kind of results, then it's definitely confusing. So yeah, stop me anytime. All right, so how do we show any upper bounds on, for example, the number of rounds that are needed to create a perfect matching? Well, upper bounds are usually easier in the sense that if you want to show an upper bound, you just need to give me an algorithm, tell me, what should I be doing as a player to play this game and achieve what I want to achieve quickly. So give me an algorithm and then, of course, try to analyze it. So it's nice because all you need to do is just to investigate one strategy. And if that strategy works, you have your upper bound. I guess lower bounds are going to be harder because, you have to show that there is no strategy that works. So that's usually worse and more challenging because, you cannot, of course, investigate all possible strategies. So you have to be clever and show that this is not because of me not being able to create this quickly, but no matter what you do, the semi-random process itself creates some bottlenecks that cannot be avoided. So I have to wait for a long time before seeing what I want to see. Okay, so here are some journal results. So actually, this paper was appeared after many other papers that I'm going to mention, but this is kind of nice, a nice framework because they show that if you want to create any spanning graph. So I would like to create a graph on n vertices, and I don't care how this graph looks like as long as it has bounded degree, then this can be achieved in a linear number of rounds. So this is kind of important because today I'll be looking at, say, perfect matchings or Hamilton cycles. So all of that, of course, are spanning graphs with bounded degree. So the story is then all we care about in this business is a leading constant. So we'll be kind of trying to see how fast I can create it, and fast meaning, can you come up with a better constant in front of n to create your spanning graph. Yeah, so I guess that's what I said. So here are just summary of results. So I'm going to go quickly because I guess I don't know how interesting it is to just summarize the results, but just maybe mention what's known. So perfect matching is already investigated, but when I got interested in this problem, that were the bounds, and now they're better. But still, I think they're far away in some sense from each other. So we still don't know, and I don't know, hopefully at some point we will know, but we are far away from kind of understanding exactly what is the constant sitting in front of n, but we only have upper and lower bounds. We also know Hamilton cycles, and here it's a little bit, maybe sad or not sad, I don't know, story, because Hamilton cycles are challenging for random structures, and there are lots of interesting tools developed out there, such as Poisson rotations and other interesting, quite sophisticated tools. So I guess we were cursed by knowing too much initially. So of course we said, oh, let's just use those fancy tools to see, how much we can do. And that was this first paper But then we realized that actually we don't need those fancy tools. We can have a fully adaptive strategy that basically it's kind of ad hoc argument what needs to be done to achieve what we want to achieve, and much shorter, much easier argument gives a much better bound. So that may be a little shame, but that's what we did after. I guess fortunately the other paper was already published, but then some other tricks were pointed out by Alan Fries and Greg Sorkin. So now we are merging our arguments, and I guess that's the bound that probably next week or 2 weeks from now should be on archive. But anyway, so not that interesting maybe, but just a message that Hamilton cycles are also studied, but still that's the difference between upper and lower bound. So still not there yet. There's still many ideas are needed to show what is the leading constant from an event. Here it's another property, and maybe I should just really go quickly. I know I'm talking too much about those results, but just in case you care, we also understand how long does it take to create a fixed graph G that has the degeneracy D. So degeneracy simply means that how is it possible to order my vertices in the graph in such a way that I have very few edges from every vertex to the left. So that's kind of important property, which is important for coloring problems. But here it's also important because when I'm constructing a graph with degeneracy D, I can achieve this by kind of iteratively creating larger and larger graphs, and then this permutation is helpful. So in the original paper, they proved some upper bounds and conjectured lower bounds, and with some other group of with some postdocs and Andrzej Ruciński from Poland, we managed to prove the conjecture. So now we know exactly how long does it take to achieve a given small graph, not a spanning graph on any vertices, but pick your favorite graph. I don't know, let it be Peterson graph. You want to create a Peterson graph in your random graph process, and we know exactly how long it takes to achieve it. So that's known, and also we generalize this game to hypergraphs. So that's could be useful. And here maybe just one slide. What else is now? People started generalizing this process. I think that's probably the next slide. But also we have some general results about thresholds. We have some a better understanding of independent sets and chromatic number. But in each of those papers, there are more open questions than answers. And I mentioned hypergraphs already. There are some other directions, like for example, instead of selecting one vertex and give it a square at random, we can pick a random permutation, and then using that random permutation, we can just keep adding squares using that permutation. So that for some properties are of course much better because you don't have repetitions, but for some other properties could be worse. So there are different generalizations one can think of. With my students, we also look at power of k choices, which is, I think, well-known phenomenon in computer science, that we have k choices instead of one. You can do things much faster. So k choices in this context will be giving you k random squares, and you can pick one of those and then put a circle to anywhere you want, and that's your edge. Okay, so any comments, questions? I know it was a lot, but it was just to highlight the problems, but now I think we can slow down and look at one of those properties. And then I maybe should have asked this earlier, but how long should I talk to?
15 minutes and then
50 minutes, but I don't remember when we started.
we started pretty sharp on 12.
Oh, 12, okay.
Yes,
Okay, good. So,
12 or not, or one.
okay, so yeah, 12:50 or something. Yeah, watch my watch because I can talk forever and that's probably not a good idea. But yeah, like there are lots of things to talk about, so I can just stop somewhere, but hopefully not in the middle of the argument, but I'll try to stop in a good place. So I think now we can slow down and look at one of those properties, and perfect matchings could be, interesting place to start. I mentioned that we can emulate or we can simulate the classical Erdős-Rényi random graph process by playing randomly, but also there's another process which is studied a lot, well, less than Erdős-Rényi, of course, but still extensively studied process where every vertex selects independently k vertices and connects to them. So I don't know if that makes sense. So we can think about a directed graph. Every vertex creates k edges to k random vertices in the graph. So I select k random neighbors, but some other every other vertex selects k random neighbors. So I could potentially be picked by someone as well. So the minimum degree in this graph is, of course, at least k, but the average degree is I guess 2k. So you expect to receive, k edges from outside as well, but you might not get any. Or you might get more, so that's fine too. So that's a semi-random process. And again, they was extensively studied. If you can mimic this process, and I'll show you, I guess, in a second how to do it. It's very simple. If you can mimic this process, then of course you can just use results about this process. And for example, if we know that if k is equal to say 5, then k out process has perfect matching, then of course I can just mimic this process. So close my eyes, just do what needs to be done, and at the end of the day you have instead of looking at a semi-random process, I'm actually have an instance of a k out process, and then if that has a perfect matching, I'm happy. So that's how we can kind of translate results from k out process to our scenario. So how do we do it? Well, that's very simple. If I want to say mimic k out process with k equal to 3, then what do I do? The first k squares, I'm not even looking where they are. So it's kind of silly, right? But I'm not even looking where they land. I always connect them to the first vertex. And then the next k random squares are connected to the second vertex, and so on. So of course, what I'm creating is k out process. So it's kind of silly because I'm actually not even watching the squares. I'm not watching the game. I know my strategy up front before the game starts. I know that the first k squares will be on the first vertex, the next k squares will be on the second vertex. Sorry, the next k circle will be placed on the first square, and so on. So I know where I'm placing those squares before the game starts, which of course is very silly, but it's already a very good strategy because we know that k out process is nice. It has a perfect matching asymptotic surely when k is at least 2. When k is at least 1, and by the way, it's sharp, so if k is equals to 1, then of course we won't have it. There are some structures that will prevent the perfect matching. Yeah, very simple ones. I don't know, what could that be? So maybe like there are 2 vertices of degree 1, that are they'll go into the same place. You won't be able to create a perfect matching with that, because those two edges have to be there to make happy those two vertices, but then they cannot be there because then the other vertex will be attached to two edges of a perfect matching. So yeah, so this result is sharp, but that of course we don't need for our argument, but it shows that 2n rounds is enough to create a perfect matching. So that's nice, but of course you can actually do even better. So I don't know, maybe I'll skip it, but we can mimic some other more complicated process and actually go down to 2 plus 2 over e, which is better than 2, but still kind of playing almost without thinking. So that's one other observation. But yeah, I'll skip it because it's maybe not that interesting. But the thing is that that was the bound that was announced when I got interested in that. And here is our result, which shows that I can do it much faster. And the upper bound that we have, it comes from the solution to the differential equation. So it could be a little bit, interesting, maybe surprising that our bound is achieved by solution to the differential equation, but you will see in a moment why. I think this is kind of interesting. And of course, the method I'm going to show you can be applied to many different algorithms. That has been applied to many different algorithms. So this is a nice tool to analyze processes where you need to track of some random variables during this the whole process. So I hope that will be interesting, and you will be able to use maybe this method, this tool for some other problems. So I use it quite often. So we will have a fully adaptive algorithm. So the algorithm is not silly, just placing circles, on one by one, but rather watch the game and try to do something smart. This algorithm that is, of course, is randomized will give us nice upper bound, and essentially, but I guess I'll show you the algorithm in a moment. It kind of tries to build the matching gridly when it's possible, but if not, then we'll construct some short paths, which are called in this business augmenting paths. So some short paths which will be useful to kind of improve our situation, right? So the easiest scenario is that if I have a augmenting path of length 2, so I have two edges that are glued together. Of course, I cannot take both edges to the perfect matching or to the partial matching, so I cannot use both of them. But this path is useful because if there's another extension of the path, I can always swap and ignore an edge in the middle that is present in a partial matching and add those edges on the side and improve my quality. So that's what we're going to do. So suppose that, at some point I have some partial matching. So I'm happy with those 3 edges, but now I still have lots of vertices unsaturated down below. So what can I do? Well, first of all, if the square lands at the bottom, then I'm super happy, right? I can just simply connect to another vertex that is at the bottom, and I have another edge of a partial matching that I can just move upstairs, and I'm happy. But again, why do we just not try to wait to be lucky? Well, because it's a coupon collector problem, namely, if I have a lot of vertices below, then of course, with high probability I'm landing there, which means with high probability, I can extend my partial matching to something bigger. But of course, eventually the set will be small. And if that set is small, I cannot just wait for those vertices to be picked by the squares, because if I have k vertices left, then I expect n over k rounds. So for example, if I have only 2 vertices left, I expect half n rounds to actually hit one of those. So if I sum it all together, I get this n log n steps. So I don't want to wait for these vertices to be picked. I have to do something smarter that is able to absorb those vertices faster than that. So what do I do? Well, if some square lands on top, which again, if partial matching is large, that will happen quite often. If vertex is picked from the top, what do I do? Well, my strategy will be to select one of those vertices uniformly at random from below. So I pick it and connect to the vertex v at random. And now, why is that a good move? Well, look what happens. It creates a red spot here. I'll call those vertices red, I guess. It creates a red spot over there, and that red spot is actually a very good spot. What does it mean, good spot? Well, if in the future a square lands on this red vertex, I'm super happy. And of course, that won't happen immediately, but a lot of squares will be placed on top, so a lot of red vertices will be present on top, and I'll be hitting those vertices often. And when I actually do that, what do I do? Well, you can imagine what do I do. Again, I'll be randomly because I would like to be able to analyze it. So randomness I can analyze. Deterministic is always a bit harder, but you can do it, and maybe I'll talk about it too. But yeah, if I do things randomly, then I like it a lot, because now, of course, we have the augmenting path of length 3, so I can ignore that edge. I won't need it at all, so I can just remove it or think about this remove. It doesn't matter. I'll just, instead of keeping this edge in the matching, I'll keep those two, and I improve my partial matching. So that's what happens. And again, here is the strategy. I think we've seen that slide, so I know it's probably nothing new here. But I'll show you. This randomized, the analysis of this randomized algorithm, which gives slightly worse upper bound. So it's not 1.205, whatever. It gives us a little bit more, but I'll be playing randomly, and that will be easier to analyze. But in order to squeeze the last drop, we can actually, as I said, deterministically do the extensions. So what does it mean? If something lands on the perfect on a partial matching, we'll be going to the vertex with minimum degree at the bottom. So the reason, again, maybe I should go back, and we'll see it in a moment. When I'm doing these extensions, what's going to happen? Well, if I absorb, if I take this to the matching, this to the matching, then I am going to destroy some of the red spots, right? Because some other vertices there, they could be connected to the vertex V. So I don't like that, because I'm happy because I improve the size of my matching, but I also destroy some red spots. Not this one. This one, of course, is going to be destroyed, but there's some other red spots that are connected, that are associated with vertices connected to V. They will be also gone. So I would like to keep the number of red places to be as large as possible. So playing randomly is not good, because then I might from time to time destroy more than I could. But if I play greedily, then I destroy as little red spots as possible. But I'm not going to analyze it. It's slightly more complicated, but of course doable. And one also technical complication is that I'll have those phases because in the first phase I'll be placing vertices of the on vertices of degree 0, and then I'll have only 0 and 1. Then when I'm done with this phase, I'll have a vertex of degree 1 and 2, and so on. So you have to glue together your differential equations. It's of course not complicated, but the code becomes more complicated if you want to analyze it. But anyway, so to get that bound, we went all crazy, and we went to whatever 1,100 phases, and then we stopped and just finished the job with a randomized algorithm anyway. But just to keep deterministically for up to creating a degree 1100, and then we gave up. So yeah, so here is the differential equation method, which hopefully you will like. So it was developed and designed by Nick Wormold at some point, a few years ago, to solve some important questions. But now it's a standalone tool that is applied to many different papers, many different results from different fields. So the idea here is that you would like to understand your random process. So you associate random variables with this process. So depending what you're doing, like in our case, I'll track how many vertices I have already matched. That's my one random variable xt. And then how many red spots do I have? That's my other random variable rt. So it's very simple process, because I'm tracking only these two random variables, and then they can actually tell me almost everything, if not everything, about this random process. So I will know what are the chances that I'm getting new edge of the matching, what are the chances I'm getting a new red spot, or how many chances I have like I lose some red vertices. So I can understand what's going on only by looking at these two random variables. And of course it's a random process, so these random variables are random variables, right? They have some distributions, but the beautiful thing is that and I don't know if I have a slide on that, maybe I don't, but that could be a nice slide. So how the method works? So it's kind of interesting because, well, you do the following. First, you say, okay, I'll just be not so rigorous for a moment. Let's just go crazy, and let's assume that my expected changes are what really is happening. So I'm kind of thinking, oh, it's not a random process. Let's just pretend for a moment it's a deterministic process. So everything moves as the expected value tells me. And then I'm saying, great, that's of course big cheat. I'm not allowed to do it, but oh well, let's do it for a moment. And then I can think about, oh, but then n tends to infinity. So I don't have a difference equation. I have a differential equation. Oh, great. Then I can solve it. I can find, where is the solution. So the idea is that, you have your random variables, and you solve, for example, the number of vertices matched. You get something like this, let's say, from the solution to the differential equation, and then the number of red spots, I don't know how the number of red spots look like, probably goes up and then goes down, or something like this. So you solve your different equations, you get this. And now, of course, that's all non-rigorous, but now you go back and apply having a zoom on equality and modify your random variables, and the conclusion is you have a proof, and that's a rigorous proof, that there exists a little envelope around your deterministic solution to the differential equations. And the envelope is tiny, it's asymptotically invisible, so it's a smaller error term. But you prove that there is a little envelope around those deterministic functions, and then your random variable with high probability is trapped in that envelope. So you get that asymptotically almost surely your random variable xt has to be trapped during the whole process in this envelope, and your random variable rt is always trapped in there. So you don't know if it's overestimation or underestimation, but you do know that with high probability it's going to be trapped there. So it's a really nice tool, and you can analyze many, and people do analyze using this tool. You analyze and you have.
Do you have class until one?
Yes.
Yes, we have something until one.
Okay, big, okay, no problem.
Yeah,
Yeah,
thank
but I
you.
was supposed to teach you at once, so I guess as soon as you finish,
All right.
we are sitting here, but
Oh.
it's not our class.
Okay.
Thank you.
All right. I have a hard deadline. Hard to stick. Yeah. So anyway, we can stop. Yeah, in 8 minutes, I guess. That was according to the plan. We have now we can actually do this, what I mentioned. So here we look at, what is the expected change in my random variable, and as you see, it's kind of relatively simple, right? Because one more time we can actually go over this. Why not? Maybe for fun. So what are the chances that I land outside at the bottom on the vertex that is unsaturated? Well, I have n minus x. I have x versus saturated, n minus x not saturated. So with probability n minus x over n, I land downstairs. And if I land downstairs, I have 2 extra vertices. That's great. But if I also land on the red vertex, which happens with probability r over n, I also get 2 extra. So that's the expected change, how many new edges in a matching I expect in around t. And they're a little bit more complicated, but the same art, you can just go over that. We get the expected change for red vertices. And I can just again do this illegal thing, namely say, okay, let me just rescale everything, rescale the time, rescale the value of the random variable, and solve the differential equation. Then that's my system of differential equations to solve. X, yeah, that's the typo, I guess. I don't know why is that. So X is rescaled X, R is rescaled R. So I guess that should be R. So we have system of differential equations, and we also have the initial condition, because at the beginning we have no edges in the matching and no red edges, no red vertices at all. So I have that, and you solve it, and then you get what I promise you by the method. So you don't need to do any job. That's a beautiful thing. There are some ways you can actually do more work and squeeze the last drop out of the method. But if you don't want to use, if you don't care about, for example, error terms and whatnot, you can just treat it as a black box. You check that your function is a Lipschitz, whatever. It's just easy condition to satisfy, and then check. You know that, for example, the maximum change is bounded because, for example, for this Hebding-Zoom inequality, we need those things. So we kind of understand why we need those assumptions. But if you check all the properties, which are always or usually very simple to check, then you're good. So, for example, here the maximum change is kind of trivial. You never get. You never change random variable x by more than 2. Red is a bit more complicated, although, because if I destroy some vertex, I can absorb some vertex. Maybe there are lots of red edges, red spots pointing to it, but you can show easily that, say, at most logarithmically many red places go to a single vertex. So the maximum change is logarithmic, which is still small and is enough for the method to be applied. So yeah, so this is what we get. So I don't know, I have 5 minutes. So I don't know, do we want lower bound? Yeah, I think maybe I can mention lower bound quickly. The trivial strategy, the trivial observation is, and trivial lower bound is half n. That's super trivial. You cannot have less than half n edges if you dream about perfect matching. So definitely we need to play a little, at least half n rounds. But of course you can do it a little bit better. And the interesting thing is that there are two necessary conditions, and both give exactly the same lower bound. So the first condition is, well, I need to have a graph of minimum degree at least 1 if I dream about perfect matching. But then if you ask me, oh, forget about matchings, just make your graph to be of minimum degree 1, so kill all isolated vertices, then of course that's the easy problem. I know what to do if I want to destroy all isolated vertices. So in each round, square arrives somewhere, and then sometimes it kills one isolated vertex. I'm happy with that. Sometimes, of course, it won't. So what do I do as a player? Well, I am always going to place a circle on the isolated vertex if my goal is to make a graph to be of minimum degree 1 or more. So I'll be playing greedily on isolated vertices, and then I can analyze this algorithm and see how long it takes to achieve it. And then another property is that, well, every edge in my graph connects a circle with a square. So I need to have at least half n vertices with at least 1 square. So forget about circles. I don't really care how you play. I'm saying random, semi-random process has to create at least half n vertices with at least 1 square. And that, of course, is not going to happen after half n rounds. It will be a little bit longer. It's actually easy to see that we have e to the minus cn vertices, or maybe I should say ct over n, ct over n isolated vertices at time t. So if I want this to be well, times n, if I want this to be half n, I need to pick t to be natural logarithm of 2 times n, I guess. So the number of isolated vertices goes down in a coupon collector problem. So the number of coupons that were not visited yet is a decreasing function of t. Yeah, that's like this, I think, right? So I was thinking about n t being c times n, but yeah, if t is just t, then I think that's kind of how much you still have left to do. So anyway, long story short, both properties are giving me the same lower bound, natural log of 2 times n. So that's how many rounds we need to do it. And we did something smarter. I don't know if maybe that's the last slide. Do I have? Yeah, we kind of did something a little bit smarter. We proved again using the differential equation method that if you look at the semi-random process, there will be lots of vertices with only 1 square, and the corresponding circle will have at least 1 square on top of them. So there's nothing I can do. The process will create lots of these structures, and those are bad structures for the player, because I cannot use both squares for my matching. If I use this edge for my matching, I won't be able to use that one or that one. But if I use one of those two, I won't be able to use that. So this gives me a boost to my lower bound, because again, if I cannot avoid these structures, then what does it mean? It means that the sum of my squares will be useless. I have to have at least half n vertices with at least one square, but actually I need them slightly more because some of them will be useless. And that is I know it's very fast and probably not clear, but that gives us this another boost. So we get this whatever 0.9 instead of 0.69. I don't know where the bound is. Maybe I'll go back. Yeah, 0.93 versus 0.69 that used to be before. So yeah, maybe I'll stop here if we have to leave in 9 minutes. So thank you.
Right, questions?
Yes.
This might not be a very well-defined question, but in general, is there any sort of conjecture about how much better you can do than, let's say, like the Erdős-Renyi thresholds with like monotone, just generally monotone properties?
Yeah, I think so. So yeah, so I think this is kind of interesting to see how much we can get extra on top of playing randomly gives us. And I think at least in those two examples, we see that we can do much better. Well, much better meaning like logarithmic factor better, which I guess is much. But some other properties might be different, right? Might be that playing randomly is actually best possible. And I don't know if I know any of property of that, but definitely I think people got interested in, and initially we thought that maybe chromatic number is a good thing, maybe because chromatic numbers is kind of difficult to analyze because some local properties and global properties play a role. And for example, this famous result of again Erdős is that you can create a graph with high graph and high chromatic number. So those are all kind of surprising things that deterministically is difficult to do. So we thought that maybe chromatic number could be an example where I cannot do anything smarter than just playing randomly. But I think for chromatic number, fortunately, it's not the case. It turns out that it's better to create a large click and then boost my chromatic number because of that. So that still playing randomly is not too bad, but I can do better being smart. But yes, certainly I think this falls into this whole business of power of k choices, but here it's kind of power of being smart. Is it good to be adaptive, or maybe smart is maybe not a good word, but adaptive at least and non-adaptive. So I think that's definitely a good direction, and I think we've seen some examples where we can do better by being adaptive, but I think I will be interested in to know what are the properties that you can actually the best you can do is being random.
I have a question in terms of like what is the motivation for considering, like in general, semi-random processes? Why they came with recently? Is it like motivated by something like happening?
I don't know if they had, initially they had some motivation, but I think I would guess that the attractiveness comes from the fact that it generalizes many other processes. But in some sense, but it gives, because it's kind of different processes that we never thought about, they're connected. Now they're under the same umbrella. So I think that's one probably interesting thing about it. And then I would say that also it falls into this big category of I would say maybe online, offline as well, because you can play offline or online. And also, I don't know if you're familiar, but again, I'm not familiar, but a lot of people in computer science really care about this notion of competitive ratio, and like some edges or some like server process and whatnot. So like there's some property you would like to achieve, but you have to make a decision right away, right? So for example, again, if I want to have a load balancing, you have your servers and your clients, you want to assign your clients in a nice way to servers. The best, of course, idea would be to just listen to all the requests and then make a global load balancing and then make a decision. But what computer science really like about these kind of questions is that I cannot wait to the end. I have to make a decision right away. So the client comes and says, give me one of those 5 servers. I need to run my job on one of those 5 servers, and you have to make a decision which server you assign to that person. So yeah, like there's a whole industry in computer science, people talking about it, and many results on that. I think it's called competitive ratio. So you look at the offline version, which is of course better, online version, which is worse, and then you try to find an algorithm that is the ratio between online to offline is as best as possible. So this is really a kind of big territory, and this process they like a lot because they say, yeah, this kind of similar thing. If I can wait with my circles to the end, I can do much better job, right? So for example, perfect matching, it's a much easier question because I need to have half n vertices with at least one square. But if I can wait for my circles, I'll just wait for that moment. And at that very moment, I say, stop. In previous round, I couldn't do it because I didn't have enough, vertices covered, but now I know. So I have n vertices with at least one square, and then I put my circles accordingly, and I'm done. So offline version is easy. This log base 2 is exactly the value for the offline version. And now, what is the competitive ratio? How much am I hurt? When I need to make a decision right away. Yeah, I don't know if I'm answering your question, but I guess that I think they really like these kind of problems because those are very real life applied questions, right? If you wait and with your decisions, you can usually do much better job, but the life is not as nice to us, and we have to make decisions right away. And yeah, here the question is how bad it is. So first of all, what should I do when I need to make a decision and I don't know the future? But of course, I have some assumptions about the future, mainly that I know my squares are arriving uniformly at random. So of course, I'm trying to use this, but I don't know where things are going to show up. But I have to make a decision right away.
So I guess we're running out of time, and so let's thank the speaker again.
Thank you so much. So I'll disconnect.